Hi guys, in this video we'll pick up here with letter C. Reactions of alcohols with SOCl2. That is known as thionyl chloride, or PX3, where X is halogen, a phosphorus trihalide. A reaction of alcohols with either one of these type of reagents will give an alkyl halide. Now, we saw earlier that reaction of alcohols with HX gives alkyl halides. So this is an alternative way to make alkyl halides from alcohols. And it's better than HX when you're working with primary alcohols. It's also useful for secondary alcohols. With a tertiary alcohol, it's typically a very easy reaction just to use HX. This is an SN2 mechanism typically. In this mechanism, the OH group is activated in a similar manner as it is with tosylates. We will see that. Then we also need to understand the stereochemistry. If we use a chiral alcohol. So, if we take an alcohol with either PCl3, phosphorus trichloride, or thionyl chloride, we convert the alcohol to the alkyl chloride. If we use PBr3, we'll get the alkyl bromide. Now, SOCl2 is specific for just the chloride. You're never going to see an SOBr2. Thionyl chloride is very common. The other halides are not. By the way, we'll also see thionyl chloride later on when we convert carboxylic acids to acid chlorides. Now, you also don't usually see PI3, although it is possible. PI3 is not a stable molecule. So usually you just see these here. Let's do the mechanism with thionyl chloride. Okay, thionyl chloride has a structure like this. Now you should know that the sulfur has a lone pair here. Of course, the oxygen has 2, chlorines each have 3. There's thionyl chloride. It's actually, well, somewhat similar to tosyl chloride, but tosyl chloride we had SO2. Yeah, okay. Where thionyl chloride, we just have 1 oxygen, sulfur double bonded to 1 oxygen, and then the other side is also another chlorine, as opposed to the toluene group. But again, the sulfur is electron poor because you have chlorine pooling, oxygen pooling, lots of partial positive on the sulfur. Yeah, as we would expect from inspection of the structure and polarity. That sulfur is electrophilic. The oxygen of the alcohol will attack. Okay, attack the sulfur. And if you remember, we said before, in such a case, nucleophilic addition, we're going to move the weaker bond away from the atom we attack. The weaker bond is the pi bond to oxygen. And that's going to give, let's have the oxygen, the H is there, yeah. 1 lone pair remaining, the oxygen now bonded to sulfur. Electrons up onto oxygen. Now have 3 lone pairs on oxygen, arising from that arrow movement there. We have chlorine and chlorine. And charge, the oxygen is minus and the oxygen here is positive. Nucleophilic addition. All right. Right. We had a similar step previously. Now, anytime we can make a pi bond and kick off a leaving group using a lone pair, easy and fast. Okay. Note there's no base here to take care of a proton. The only thing we can do is these electrons back down, kick off. We actually could kick off the chlorine or the protonated oxygen. Reversible, yeah. But instead, let's kick off the chlorine, one of them, and that's going to give us oxygen, sulfur, double bonded to oxygen, 1 chlorine, H here, positive, plus Cl minus. All right. Now, where are we trying to get? We're trying to get the alkyl chloride, chlorine bonded to this carbon. Well, look now. We have a positive oxygen. Looks like a good leaving group. Here's a nucleophile we just generated. Now these electrons can attack the carbon and kick off the oxygen. And that is going to give that product plus OH, all right, 2 lone pairs now, all right. Now, hopefully everybody knows why there's 2 lone pairs here, all right. Where did the lone pair come from? If you do not, you need to understand your arrow movement, okay. I would like to assume that everybody understands arrow movement and recognizes where lone pairs are coming from, and you're not just memorizing things. Resulting structure comes from arrow movement. Okay? Give this here. I'm not showing all the lone pairs. Okay, that sulfur has 1 lone pair. All right? That. There's our product. And right here is your SN2 backside attack kick, and this oxygen is sort of activated, sort of like a tosylate. It's also protonated. It's a good leaving group there. Now, this byproduct breaks down. All right. The complete byproducts here are SO2 and HCl. Now, how do we get those? And by the way, both of these are actually gases under these conditions, and they can be driven off. What did we say before? Anytime you can make a pi bond with a lone pair, kick off a leaving group, pretty easy to do. All right, that's about the 3rd or 4th time I've said it. We'll say it about 1,000,000 times this semester. Always look out for that. Right here, lone pair can move in here, kick off that chlorine. And that's going to give oxygen. The H is there. 1 lone pair remains. Double bonded to sulfur. And that is double bonded to oxygen. There's a lone pair there if we want to keep track of that. 2 here, positive here, plus Cl minus. All right. Now we can go neutral by this anion, these electrons taking the H. These electrons staying here, and that produces the 2 byproducts I told you were formed in this reaction. With the Lewis structure for SO2, basically you see it here after you put the lone pair, the second lone pair, back on that oxygen. This idea that anytime we can kick off a leaving group with a lone pair and make a pi bond, that's driven by entropy. One molecule breaks down into 2 molecules. All right. Some very fundamental steps that we're going to see over and over. Now, if you use something like PCl3 or PBr3, one lone pair there, yeah? Phosphorus is right below nitrogen. That phosphorus is partial positive because the 3 bromines pooling. These electrons attack phosphorus. There's no pi bond here. You're just going to immediately kick off one of the leaving groups. And that's going to give you oxygen bonded to phosphorus, 2 bromines. Okay. But then that Br minus that we've kicked off can come back. See, this oxygen looks activated. Kick that off. And we get our alkyl bromide there. And here you end up with this here. Now you could think about here, these electrons come in here and kick this off. And you could sort of keep going. The problem is at this point, you really can't do much else. But if you pour water in here, then water could react with this, and that's sort of the end. But we won't keep going there. We did it with SOCl2, thionyl chloride. We'll see this again. Thionyl chloride's a little bit more common here. But your PBr3 and your PCl3, okay. This is sort of predict the product, okay? How do you convert an alcohol to an alkyl chloride? Well, you got 2 reagents right here. You could also do it with HCl. So these are alternatives. Okay, now we can use this information for predict the product reactions, maybe multi-step reactions. Now keep in mind that when we made the alkyl chloride, we did an SN2. We did chemistry at the carbon. Backside attack. All right. Same thing if we react with PCl3 or PBr3. We're doing SN2. Chemistry at the carbon. We're going to get inversion. So with PBr3, we should end up with actually that alkyl bromide. All right. The OH becomes activated. All right. Then the bromine attacks backside SN2 with inversion, right? Then if we come in here with potassium cyanide, let's draw full structure there. To kick off the bromine that we put on there, we're going to get back to forward bond with the cyano group. So we did 2 SN2s. All right. I'll let you do the next one for homework. All right. Keep in mind, converting the alcohol to an alkyl halide, sometimes you do that because you want a better leaving group. You know, there's multiple ways to get better leaving groups, different leaving groups. Maybe you want different stereochemistry. So in this two-step sequence, converting this to the alkyl bromide was really just converting it to something that can act as a leaving group without the need for acid. Alternative would be to convert it to a tosylate, which it looks like the next reaction is what's going on there, yeah? Okay. Roman numeral 2. Looks like we're moving on to a different topic. What was Roman numeral 1? Okay. Again. All right. Now my outlines are not always going to be, you know, if you want to put a Roman numeral 1 here because that's the way it was over here. But next, dehydration. It actually doesn't say dehydration here, does it? Well, it kind of does. It says minus water. Looks like dehydration. It's an elimination reaction. We're dehydrating by an elimination reaction. So things are presented a little bit differently. But that's actually good because there's different types of terminology we need to know. And we need to work on reading headings, understand what we're doing. That helps us organize our thinking, organizing our learning approach. So let's look at dehydration of alcohols to give alkenes. And the first way is using acid, either H2SO4 or H3PO4 phosphoric acid or HF. You're not going to be able to use HBr or HCl or HI. Okay. So you can't use the other HXs. HF will work because F- is a poor nucleophile. When we're doing this chemistry, we do not want a competing nucleophile or we may get substitution. And the anions that go with these strong acids will never do substitution in our course. All right. So if we look at this, if you take this alcohol here, which is a chiral alcohol, heat it with sulfuric acid, we can get this alkene. All right. Dehydration. We've lost water. Now note that we're going to get the trans. Okay, remember the terminology here when we're making alkenes. It's the more substituted. Okay. Thermodynamic product. And the more substituted alkene equals the Zaitsev. How do we want to spell Zaitsev this semester? If you spell it with a Z, it's usually Zaitsev. But sometimes it's spelled like, actually like that. There's multiple spellings for Zaitsev. Okay, it's thermodynamic. It's the more substituted product. It's also going to be trans with the larger groups opposite. So it's not going to be cis. And then the less substituted, if you remember, is, and if you pause the video, the Hoffman product. As we said in Organic 1, anytime you do an E1, well, anytime you do an elimination of an alcohol with an acid, it's always E1. And an E1 always gives the most stable product possible. And it's this one, as opposed to one of those. Now, both of these could be called Zaitsev products, but of the two, the trans is going to be the more stable Zaitsev product. Why is it E1? Well, E2, of course, requires what? A strong base. And if we're doing a reaction with strong acid, you certainly don't have a strong base. So if you're doing elimination and it's either E1 or E2, could it be anything else? At this point, I don't think so. Can't be E2, it must be E1. Yes, mechanism here. We have H plus from our strong acid. Protonate the alcohol. We have the conjugate base of sulfuric acid. It is a weak base, very weak base. Certainly is not going to do an E2, and it will never act as a nucleophile. So what else can happen to this protonated alcohol? The only thing that can happen new, other than reversing, is the oxygen could just leave, and that would give a carbocation plus water. I'll show minus water here. Now the next step, well, this thing's actually going to rotate now. Sometimes rotations are shown in mechanisms, sometimes not, but let's rotate it. Instead of syn, let's make it anti. Remember conformations of alkanes? Okay, the thing can rotate, yeah. This is favored. But then, next step is, this will act as a weak base, and we can take one of these H's, and these electrons move in, and that gives us our pi bond back. But we also form, or reform, sulfuric acid. And thus the sulfuric acid is our catalyst for the dehydration reaction to give the alkene. All right. We also made water. I just showed it right here. Eliminated water. We produced water. Now, some instructors instead would use water to take the H. You can do that. I've talked about that in Organic 1. If you use water, you're going to form H3O plus, and this anion would just sit there with it. How about if we say HSO4 minus? And you'll just be left with that. But of course, that's how sulfuric acid exists anyway. And it's the same story for those who had me for Organic 1. I actually like to reform the actual acid molecule to clearly show that it's being reformed and to clearly show that it's a catalyst. Whatever works for you. I really like to show both. So you will have seen both. Okay. E1, carbocation chemistry. All right. Product here. All right. Got to assess the reaction. You got an alcohol, you got strong acid. What can happen? Well, there's no nucleophile. HF is one of those acids that will dehydrate an alcohol. What else could happen here? Okay. That right there is something for a note card. You got to be able to look at that and understand what is the reaction that's going to take place here. There's a little bit of memorization there, but it's more of an assessment. All right? Structured memorization. And then you have other things you can include on your note card, like, you know, E1 always gives Satsef most, you know, and any other things that go along with an E1. And the product here, you can pause it. All right. Work on that. I'll go ahead and show the product here. Right there. It's going to be, the alkene's going to be over here, so it's tri-substituted as opposed to here. Keep in mind with carbocations, what are they prone to doing? Rearranging. Okay. Didn't see any rearrangement here, but perhaps on the next one. Okay, let's look at B. It must be another way to dehydrate an alcohol to an alkene. It is using POCl3. That's often pronounced pocyl, pocylpyridine. Here the OH is activated as the dichlorophosphate ester. And it's typically an E2 mechanism. It's another way to dehydrate an alcohol. Particularly good for primary alcohols, because if you try to dehydrate a primary alcohol with just strong acid, it's very unlikely, or it's rather difficult. Mainly because it's very hard to form a primary carbocation. Instead, now this is POCl3. It's similar to thionyl chloride. And again, the alcohol attacks the phosphorus, electrons up. Boom, 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 boom. All right, electrons back down, kick off one of the chlorines. See the consistencies here in some of these reagents. A nucleophilic addition. This is going to be an elimination. Boom, 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 boom. Reform the double bond. We have two chlorines, positive on oxygen, and a Cl minus. Now we could envision maybe this attacking here and we're getting an alkyl chloride. like very similar to over here. Okay, this didn't have an oxygen here. The difference is we include pyridine. That's probably two equivalents of pyridine. Because one equivalent of pyridine probably takes care of the proton here. Okay. And we get pyridine hydrochloride. I'm not going to show that. We showed that earlier. You've got that there. Let's focus on here. We're trying to do an elimination. Okay. At this point, a second equivalent of pyridine can come in here and do an E2 elimination. This looks like an OTOS. Okay. Now there's not that sulfur with two bonded oxygens, but we got these extra two chlorines which are really pooling here. E2, base takes the H, electrons move in, leaving group off, right? And that gives us our alkene here. Now in this reaction we produced two of those, one right here and then another here. We've got a Cl minus, which that's it here, I just redrew it. But then the other minus is this leaving group. Which looks like it may break down because we can make pi bond and kick off a chlorine, but I'm not going to consider that here. But see, we generated an acidic proton along the way, so we had to take care of that. I think this requires two equivalents. Ultimately, pyridine must be strong enough to do an E2 because it's happening here. And the evidence, a lot of the evidence suggests it's E2. Again, there's an activation of the OH group in some matter, classical E2. Do you remember your stereochemical requirement for an E2? You remember the leaving group and the H must be coplanar, with anti-coplanar being preferred. Really didn't have to consider that here. Now in these cases, yeah. So again, some review from Organic 1. Okay, I'm debating whether to continue on here. I think I will. All right. Let's do about half of this next topic. Roman numeral 3. It's really here. Oh, alkylation, formation of ethers. Okay. Instead of replacing the OH group or eliminating it, we're going to keep the oxygen, but we're going to put an R group on the oxygen. We're going to alkylate the oxygen. And that's going to give us an ether. Okay. This general synthesis is called a Williamson ether synthesis. Let's look at it. The first thing is if you have an alcohol and you want to put the alkyl group on, usually by an SN2, we first have to have a better nucleophile, because a neutral oxygen, a neutral OH group, is not a good nucleophile. But the oxygen anion is. Now, by the way, when you look at this, you've got to see that this is O minus and Na plus. Okay, that's O minus there. You got to recognize spectator ions could be shown there. It's just like if we showed potassium iodide. Okay, you got to know that that's I minus, right? And K plus. So you see I minus. And organic chemistry, we never do anything with group 1, group 2 typically. And so just it's I minus. That doesn't mean we can't show things like this. That's Cl minus. All right? That's O minus right there. It's negative oxygen. This is neutral oxygen. A common way to convert this to the oxygen anion is using sodium metal, oxidation state of 0. Okay. This is actually a redox reaction. It's not a traditional acid-base. And thus we're not going to show a mechanism. It's a radical reaction most likely. The fate of the H is to form hydrogen gas. All right. So if you want to balance this, you're welcome to it. I think you're going to need 2 of these to give 2 H's here. You're going to need 2 sodiums and 2 of these. All right. Free there, no charge for balancing that. By the way, what do we want to call this? It's not an alcohol. Well, what do we call this? Hydrogen oxide. Combine that hydroxide. Well, this is an oxide with an alkyl group. It's called an alkoxide. All right, our alkoxide anion. Most common way is to react with sodium metal. You can also use potassium or other metals, but sodium is by far most common. We can also use sodium hydride. Here the H is minus. First time we may have seen sodium hydride. I know in Organic 1 we saw sodium borohydride, right? This was a hydride source because it will kick off the H and the 2 electrons. We'll see that later. This is a standard acid-base reaction. If we show our OH bond out, these electrons take the H, these electrons stay behind. Let's get rid of that. We would then have 3 lone pairs and a minus. And we also form hydrogen gas here, but we see that right here. So, but if you make the alkoxide, you can then do simple SN2 chemistry. Sodium is going to convert this to the anion. Can I just convert it to the anion without redrawing anything, right? Isn't that what sodium does, the alkoxide? Then when we come in with this here, we can come in here and bam, kick off the leaving group. And we would get oxygen bonded to that carbon instead of chlorine. Let's see here. The carbon over here that the oxygen is bonded to is chiral. It is, we just did an SN2. So this is going to look like that there. And I kind of made it ugly looking with the bolded bonds, everything here. Yeah, because this over here is S, and so that there should be S. But we now have an ether. Instead of a chlorine bonded to that benzylic carbon, the oxygen is now bonded to the benzylic carbon, because the good nucleophile, which we generated by reacting of the original alcohol with sodium metal, and the alkoxide then did a backside attack, and that's how we did our substitution. We call it SN2. We made an ether, and that is a classical Williamson ether synthesis where you start with the alcohol, convert it to the alkoxide, and then come in with some type of alkylating reagent to supply the alkyl group. Now phenols are more acidic. All right, alcohol is about 16 to 18. Phenol is much more acidic. We can deprotonate these with a more simple base, hydroxide. Okay. Sodium hydroxide, potassium hydroxide, standard acid-base reaction. You know the mechanism to make the phenoxide. All right, in this case we're making water when hydroxide takes the H. I'll let you work on that for homework there. So down here you don't have to use sodium, which is actually a little bit more dangerous, more expensive, etc. We can use the more common hydroxide. With regular alcohols you have to use either sodium or sodium hydride. Okay, and if you know how to use pKa's to judge equilibrium, let's do that down here. pK of water is about 16. Which side's favored, 10 or 16? Okay, well 16 is favored. And so we get the phenoxide favored. But up here, well, if this was 16, regular alcohol, which side would be favored, 16 or 16? Well, neither side would be favored, and it actually would not be good in practice. You need at least a difference of 2 or 3 log units to be good in practice. All right. Phenols are more acidic. Hydroxide can be used. Okay. Now with the Williamson ether synthesis, we also need to be able to go backwards. And if we look at an ether, how would you synthesize this ether? That is, what alcohol would you use and what alkylating reagent would you use? Typically the alkylating reagent is going to have the leaving group. All right, it's just what we did over here. And thus coming up with a synthesis Now note here, in this ether, we just made this bond. Oxygen-carbon bond on the left side. We could have theoretically had made the oxygen-carbon bond on the other side with that alcohol and then that alkyl with a leaving group on that carbon. All right? So there's two different sides. And so over here, do you want that to be the alcohol, methanol, or do you want that to be the alcohol? Same thing down here. Do you want ethanol to be the alcohol, or do you want phenol to be the alcohol? Think about that. Okay, reading in your textbook. I'm going to ask that you do these on your own. Think about it. All right? And look at the remainder of this page. We'll pick up here in the next video, but you need to do your homework. All right? You know, really understand what's going on in this Williamson ether synthesis here. Can we go backwards? All right. By the way, I'll end here. Going backwards, we use a retrosynthetic arrow. And we can say, I'm going to go backwards and break, let's call this A here. I'm going to go back to the nucleophile plus the alkyl group now I can't just call that a methyl because there's no reactivity here. I need a leaving group. Okay? Whatever your favorite leaving group is. Now, coming forward here, we had a chlorine as a leaving group, but it could be, okay? And now we can say, I went back to two reactants that could react, and coming this way would give that product. That would be A. But what if I broke this bond over here instead? Separated the molecule here. It would be that alkoxide, and then again that carbon, that fragment with a leaving group on that carbon. Okay? Work on that. Then we'll also in the next video be getting into reactions of ethers. Okay? Once we see the most common way to make ethers. And that'll actually finish up this first handout here. Okay, guys.